All right, just to review a little bit of what we looked at on Tuesday. The basic structure of an MRI imaging system. Static magnetic field is applied by superconducting coils, excuse me, providing a field inside this cylinder about 30,000 times the Earth's field if it's a 1.5 Tesla magnet. There are many 3 Tesla magnets in practice now, but I would say the majority of cardiac imaging is done at 1.5 Tesla. And then inside the magnetic field coils are another set of coils, 3 independent coils that we looked at that are called gradient coils, which change the magnetic field as a function of position. It's important to note that they change the amplitude of the Z magnetic field. It's not that they make a magnetic field in the X and the Y direction. They just change the actual amplitude of the Z field as a function of X and Y. That's a gradient coil. And then inside that is a radio frequency coil, which is used to transmit radio frequency energy into the patient and then receive radio frequency energy from the patient when you've stimulated a signal. This is called a body coil, and this is principally used for transmission, this type of coil, and it would transmit energy into the entire torso of the patient. And then this is the receiver coil that will be switched on to receive the signal once the patient starts emitting radio frequency energy. Again, the geometry of the gradient coils, we looked at how the Z coil functions and how the X and the Y gradient coils function, and recall that the business end of those coils are the current paths that are very close to the imaging volume. The imaging volume in a magnetic resonance imaging system is approximately spherical, and the diameter of that sphere is probably about 35 to 40 centimeters. Right, is the volume over which you can make an image with reasonable resolution and signal to noise, which is fine for imaging the heart. Sometimes when you're imaging a patient and you really want to focus on their heart, you will shift them slightly in the bore of the magnet such that their heart is centered up in the middle or the sweet spot of the imaging system. We did this very simple pulse sequence. This is, NMR imaging. When you get into it, it's all about designing pulse sequences to elicit a signal from the patient that have different intensities based on underlying parameters such as flow and relaxation times. And so these pulse sequences are created, and essentially what they are is an amplitude versus time of things like RF and gradient pulses. And this is the signal that is measured on the same time axis. And recall the diagram where we showed that the signal that is measured is equivalent to the transverse magnetization vector. That's what we're seeing here, is that ring down of the transverse magnetization vector. So an RF pulse is put into the system, into the patient. From the patient, we see this RF signal coming back. It decays with T2 star, this free induction decay, or FID. And then we can elicit another signal by adding a 180-degree refocusing pulse at TE over 2, and then at TE, we will see the peak of a spin echo. And the decay of the amplitude at T equals 0 down to TE at that peak, that decay envelope goes as T2. That's the relaxation time, T2. We also looked at T1, which is the rate at which the magnetization vector recovers in the longitudinal direction or back in the Z direction. So recall when I have a sample of a patient or a bottle of water or something, I put it in the magnet. Over the course of a couple of seconds, I will generate a magnetization vector in the Z direction or in the longitudinal direction. The rate at which I can generate that magnetization is governed by this very simple solution to a first-order differential equation. It's 1 minus the negative T over T1 to the exponent, to e to the minus t over t1. And so that is a simple mono-exponential time constant, t1, which characterizes that rate. And so different tissues have different rates that will generate contrast. Short t1, we recover fast. Long t1, we recover slowly. In a similar way, once the magnetization has gone into the transverse plane, it will decay away with a mono-exponential decay, and that's governed by this simple time constant, t2, and it's about an order of magnitude shorter than t1. And you can see that, if I have something that has long t2, the signal will last longer in the transverse plane. Examples of things with very long t2 are water. Blood has a reasonably long t2. Short t2, if you get to a more solid-like substance, the t2 will become shorter and shorter, until finally when you have a true solid, the t2 is sort of microseconds long. So we got to this diagram on Tuesday, and this is a full-on imaging pulse sequence. And it has radio frequency, amplitude versus time. It has the signal that we're going to measure versus time. And then the three lines here, X, Y, and Z, are the gradient pulses. And so these are it's like a gating signal for putting current into those gradient coils. So if I look at my slice direction or the Z direction, the amplitude of this function determines the amount of current I put in that gradient coil, in the Z gradient coil. So I have zero current here, I ramp it up to some value, and then ramp it back down here. And if this diagram shows a value that's twice as high, then I would put twice as much current in that coil. And so essentially drawing these diagrams is 90% of what people do when they're having fun with MRI, is draw different versions of this diagram and then run it on the scanner and see what kind of pictures you get. This is a very simple imaging experiment here. This is called a spin echo image. The raw data to obtain the image will come from this signal here, which is the spin echo. This signal is ignored for this type of image. It happens, but we just ignore it. And you can ask yourself, well, why ignore it? If there's signal there, why don't you sample it and use that towards making the picture? And that's a good point. You should probably sample all the signal you have. But anyway, so let's take a look at each one of these lines and what they're doing. This is the most simple. The GZ, or the gradient in Z, when we pulse those two circular coils, creates different magnetic field strengths as a function of Z, and then we hold this current constant, and so that gradient is sitting in a static form during this RF pulse. So the feet of the patient, or let's say the hips of the patient, are resonating at a different frequency than the shoulders if the patient is lying along the Z-axis. And what that does is, if I have a constant gradient on during my RF excitation slice, that means that only one single plane of the patient, one axial plane, is actually on resonance. Right? So if this is 64 megahertz, and the only thing that's going to elicit a signal from the patient is something at 64 megahertz, because that's my RF, then when I turn that gradient on and I look through my patient, there will be one plane that is resonant at 64 megahertz. If it's up towards their head, it may be a higher frequency, the spins would resonate at a higher frequency. Down to the feet, a lower frequency because of the gradient. So it's that spatial distribution of the magnetic field that I've changed in a very controlled way that gives me slice selection. So already, after applying this gradient during the RF slice, I have selected a chunk of the patient that I'm going to get signal from, and it's the slice. If I just pulse this gradient, then my slice is in Z. So I have a plane that is perpendicular to the Z direction. If, on the other hand, I kept this gradient off and I pulsed the Y gradient during the RF, then I would get a plane in Y. It would be perpendicular to Y, and so I would get a coronal shot through the patient just by changing which gradient I have on here. If, on the other hand, both of these were 0 and I pulsed an X gradient, right, and that's the gradient that usually runs between the right and the left side of the patient, now there's a central plane down the patient in the sagittal plane that would give me signal. And so that would be a sagittal image. So by pulsing those gradients differently, I can select different volumes inside the patient. That's called slice selection. It's very useful, right? Because if you want to slice through the heart in an oblique orientation, such that you are in the natural coordinates of the heart, say we want a short axis view, I can pulse the 3 gradients with relative amplitudes to achieve that oblique slice. Right? That was one of the first big patents in MRI. I mean, most of MRI came out of university labs, and all of the university labs patented all of these things as they were discovering them. And so it was very expensive for companies to get in because they had to license all of these darn patents. But anyway. So once that slice selection has been achieved, we can shut that gradient off. We have now provided an RF pulse to stimulate signal from the patient, and we will get this signal out of that slice. So this will be much smaller if we have a slice selection gradient on, the amplitude of this signal, because it'll be coming from a selected slice. The next thing that happens in this imaging experiment is we pulse a gradient. In this case, we've chosen to pulse the Y gradient for some amplitude in some unit of time. And so what that does is it changes the frequency at which the spins or the magnetization vectors are processing in the transverse plane as a function of Y. So all of those magnetization vectors in the 0 coronal plane, when this gradient doesn't change the Z field in that plane, they will all stay in phase together. They'll all be pointing in the same direction and precessing at the same frequency. Magnetization vectors that are up or increased in value in Y will be precessing at a faster rate because the gradient is producing a higher frequency up there. And those magnetization vectors below the 0 plane will be precessing at a lower frequency. And so over time, the magnetization vectors as a function of Y during this gradient will evolve to produce a phase angle shift, right, dependent on Y. So if I look down a column and I look at my magnetization vectors, I look down a column as Y is changing, the magnetization vectors will have essentially a helical distribution because the amount they've processed over time is different. So let's look at the solid one. I just do that once. I produce that phase shift as a function of Y. I then apply another RF pulse to refocus the magnetization vectors due to the sort of magnetic field inhomogeneities. They'll be oscillating at slightly different frequencies. So I produce a spin echo over here with this 180. I apply the same gradient that I did here so that I'm essentially affecting the spins in one plane in Z, right, one axial plane. And then as my signal is evolving, as the magnetization vectors evolve, they will come back into phase over here to make a spin echo. And during that spin echo, I will read out the signal with a constant gradient on, and that gradient is orthogonal to both of these. It's in the x direction. So this signal is modified by the fact that I have a gradient on across the patient while I'm acquiring that signal. Okay? And this is called the readout gradient, and it frequency encodes different columns in x as I'm reading out the sample. So this is what the raw data looks like for an NMR imaging experiment. And as I sample this echo, this is my data sampling window right here. When I look at, if I take, say, 128 of these samples, and for each one I change the amplitude of this gradient, so I do 128 of these gradients. It's 128 separate experiments. And I stack them one on top of the other. It looks something like this. So this is the readout direction, right? And I get an oscillating amplitude of signal as I read out in time. So when we go back to our diagram, this is the readout, and I'm reading out across this way. Right? Each one of these rows corresponds to a specific value of the m delta gy. So m is clicking through, say, minus 64 to 64 to get 128 of them. And so we step our way through those values to produce this two-dimensional data set. And so this is the raw data. It looks nothing like, the object we're imaging, but in fact, it is the Fourier transform of the picture that we're going to create. It's the two-dimensional Fourier transform of the picture we're going to create. So when you take the 2D FT of this, you get an image. So let's go back and we'll look at these gradient coils and figure out, how does this happen? How do you make this pulse sequence? How does that generate the 2D Fourier transform of the image of the object? We'll take a look at that now. So recall we have B is our Z component of the static magnetic field, BZ, and at each point in the volume that we're imaging, X, Y, and Z, we have the following. We have the static magnetic field, which is 1.5 Tesla. And then we're going to modify that field with our gradient pulses. And the way that modification occurs is we have the gradient value, which is the change in the BZ field versus a direction. Let's just use X to begin with. So that's the rate of change of BZ as a function of X as our gradient times X, right, gives us an offset field. So this product gives us a delta B for the position X. And in exactly the same way, if we had all three gradient coils on at once, we can compute what our field strength is at the location X, Y, Z here by this formula. So we have three gradients, a position in the volume, and that gives me my new Z field. And so usually we just shorten the notation such that this is understood to be represented by G sub X. Okay, so B naught plus G sub X times X, G sub Y times Y. That's this equation written just as the gradient value. This is just a scalar number, right? So you can just give it a simple notation. So what does a Z field look like? A gradient in Z versus a gradient in Y. If Z is this direction and Y is this direction, GZ looks something like this, in the sense that as we move in the Z direction, the B field is changing. A gradient in Y means that as I move in Y, the B field is changing in that direction. Now remember, they're all pointing in the z direction. We're not looking at B sub y or B sub x. We're looking at it in the z direction. And that defines the frequency at which the magnetization vector will process through the Larmor equation, that equation that we studied before. Recall, it's very important to recall that the frequency, or omega, of the magnetization vector is linearly proportional to the B field that it is in. Remember, it's omega equals gamma minus gamma B, where B is the magnetization, or excuse me, B is the applied field, applied magnetic field. So this, we've jumped straight into the math of how the sample itself creates a time domain signal that we sample, and its relationship to the applied gradients and the position of the object. So if we're trying to reconstruct an object which is MXY, a two-dimensional object, say we've done a slice selection in Z, and we want to produce a picture which is magnetization vector as a function of X and Y. When we sample one of these, let's go back, one of these data samples here. So this, as I go along here, and this is S of t, or the amplitude of my voltage as a function of time for each sample at this point, and I'm asking, well, what is the relationship of that sample function to the gradients and to the object? So here's the object. This is MXY. If M is 0, that means there's nothing there. It's just air. You know, if M naught is large, I have some signal there. And the frequency, or the composition of this time domain signal, is the superposition of the oscillations of MXY at different locations in the sample. So, to compute what the contribution is from any given point, say X and Y in the sample, just as we saw before, I compute what is G. G sub X times X gives me the oscillatory frequency from the Z, from the Z gradient application, and in the same way, G sub Y times Y gives me the frequency in Y. And so if I look at each point in the sample and just add up all of those signals, right, then I get this equation here. And it's an integration over space, right, over dx and dy, where I look at the entire sample that I'm imaging. All of that sample is giving me contributions to my final signal I'm measuring. And so that's this integration over the plane, over the imaging plane, X and Y. The complication in here, the integral over tau, is the fact that I just integrate this evolution during the application of the gradient. And so G sub X of tau is this function back here, right? G sub X of tau is this guy. Right? And G sub Y of tau is the time domain function of the Y gradient, which is this guy. All right, so this is a simple one. It just gets turned on and then turned off. So that integral over time tells me, how to modify, or how the signal gets modified when these gradients are on. Right? So there's three integrals going on here. The integral of the time evolution of the sample during the application of these gradients, and then I integrate over the entire sample, or the entire imaging volume. So that provides me with a complex time domain signal, S of t. And essentially, what you can show is that, when you do this integral over tau of the g sub x of tau, it's equivalent to, from that integral from 0 to t is a function in t that is equivalent to the Fourier component in, say, if it's the x gradient in the x direction as a function of time. And this just works out from the math, right? If you believe that this is actually the, from what we've studied with that diagram, that this is the proper equation for the time domain signal, then you just rearrange this math and you can show that essentially what you're doing is creating the Fourier transform of the object and sampling it. And with the definition that k sub x of t here is this integral, 0 to t, g sub xt to tau, over tau. So tau is the dummy variable. We're going from 0 to some t value, and that puts us at a value of this function that oscillates as a function of t. So when you look at this is simply the two-dimensional Fourier transform of this guy, right? And this is our image, right? So that's what this is going to, the signal is going to be the two-dimensional Fourier transform. So if we look at, what that means, our raw data is this function here, right? We'll just call it capital M as a function of kx and ky. These are the Fourier components, of the function in Fourier space, and this thing is equal to the Fourier transform of our object. Okay, let's go through and visually take a look at what this means. So here's my raw data space, and remember these are my signal amplitudes as I sample across. When the x gradient is on, I'll sample across this way, right? This is my image space, and I'm modeling the image as an array, a discrete array of magnetization vectors. And each vector has an amplitude, and it also has a phase. It has a position in the transverse plane, right? When I apply an RF pulse, forgetting about slice selection for the time being, let's say it's just a two-dimensional object, I get a set of magnetization vectors in the transverse plane, and they're all pointing in the same direction. They have equal phase, so their angle in the transverse plane is equal. When I apply a y gradient, right, at time point 1, I'm going to turn on a y gradient. Then over the duration of that gradient, the spins will be, or the magnetization vectors will be traversing or oscillating in the transverse plane at slightly different frequencies, such that all of those at one y value here will, say, be on resonance at 64 megahertz. These ones may be resonating more quickly as a function of y, and these more slowly. And that will produce, for each column in this diagram, so this is the x value, this is the y value. So for constant x, when I go down and look at my magnetization vectors in y, you can see that there's a phase shift as a function of y. And it's been provided by the evolution of the sample during the application of this y gradient. So at the point 2, my sample might look like this. And then I just keep it on at the same amplitude, and let's see what it looks like at time point 3. I have twice the phase shift as a function of position in y in the sample. And so now my sample, if I just take a freeze frame and I could look at it, like this at one time point, it actually is that picture. The magnetization vectors have that relative phase shift as a function of position, which is fascinating, right? Now, if I add up the signal that is proportional to the sum of all of those magnetization vectors together back into my coil, that is essentially like applying the Fourier transform, applying a k vector to that object, and then sampling what the amplitude of the signal is. Right? So that k vector, it has a value in y. In x, you can see where we have no change in phase as a function of x. And so the kx value, the Fourier component in the x direction is 0, or at dc, whereas in the y direction where we have 2 full cycles here. And then if I turn on the x gradient, I will start generating a phase shift as a function of x in the sample. And so the orientation of the phase angles of the magnetization vectors starts to look like this as this gradient, or the sample evolves under this gradient. Right? So if we look at the raw data space and say, well, let's measure the signal amplitude as a function of time. So here's one application, right, or as a function of time. Well, actually, a better way to look at it is let's look at the data point in this raw data space. So what is the amplitude of a data point in this raw data space? At time point 1, if we were sampling it, all of these magnetization vectors would add up to give us a signal value. That's that integral over dx dy, and that value is right here. And it's a very bright value because they're all pointing in the same direction. They would add up constructively to give us a very high value. As I move or as I let the sample evolve with the y gradient on, what happens is I effectively move up in k space in the ky direction, and I sample this point at this time. And so this is, over time, we're moving in the Fourier space in the ky direction. And then if I continue with that gradient on, I just move twice as far to this point. And I would sample that point right here. And now, if I turn off my y gradient, turn on the x gradient, I start moving in the kx direction, and I sample this point, which corresponds to this orientation. So that's 4 samples of the Fourier transform of our object, which is provided by these 4 points in time. And that's this point, this point, this point, and this point. Okay. So an acquisition of a k-space line, so those were k-space points that we acquired at each one of these times. That's s of t at each point. What we're going to look at is if we turn on a gradient as a function of time and sample while that gradient is on, we effectively streak across the Fourier space in the direction that is defined by this gradient. And so when I apply a 90-degree pulse, I can apply a gradient here which will change the phases of the magnetization vectors in the transverse plane and move the sample itself to a different point in the Fourier space, so it moves down to here. And then I apply the opposite gradient, and I start, as I sample points along here, I'm moving continuously across Fourier space. So this is usually what's done. There's usually a readout gradient, and you sample across time during the application of that readout gradient, and that gives you one line through k-space. And so here we would sample one line through k-space like that with this gradient on. There's a slight complication with spin echoes in that the 180-degree pulse itself refocuses. When it's doing the refocusing, it also moves you in k-space. So, the first gradient gets us over here in the Fourier space, and then when you apply a 180-degree pulse, you actually effectively go to the conjugate position. But we won't look at that. That's a little complicated for right now. So here's a two-dimensional imaging pulse sequence in which we're going to have a readout gradient. And so during the acquisition, we'll be streaking across K space in the Kx direction because it's an X gradient. But prior to doing that, we will position ourselves at a specific Ky location by pulsing this Y gradient. So what we do is we create magnetization in the transverse plane with a 90-degree pulse, so the magnetization vectors all drop into the transverse plane. We then evolve their location in Fourier space by applying two gradients. One is in X, so the X gradient will push us over to here, and one is in Y, and that Y gradient will have a different amplitude for each acquisition, and it will push in the Y direction, so we might wind up at this location, right? The 180-degree pulse, we can just take it on faith, puts us to the conjugate location in K space. And so now we have an offset in Y, in Ky, and we're going to streak across here with this gradient on to achieve sampling in Kx. Some other interesting patterns of sampling are, the application of continuously changing gradients while you are reading out your sample. So if we select a slice, and we have now a 2D sample, and we pulse the gradients with a sinusoidally oscillating amplitude, and on the readout and phase encoding direction we slightly phase shift them, you will essentially be sampling K-space in a spiral like this, right? And so you can sample the two-dimensional K-space of the object from the center of that K-space, or the Fourier space, out to the periphery with essentially one long acquisition, right? So ideally, if you were able to oscillate these gradients fast enough and you had a long enough time, if you basically had signal, if T2 was long enough to give you signal out to here, then you could make a full 2D image with just one acquisition. And this is called spiral imaging or echoplanar imaging. Another way of sampling is also to perform a radio frequency pulse, generate transverse magnetization, and then read out with the different amplitudes on the, say, X and Y, or the readout and the phase encoding gradient set. And so what that will do is you'll read out along a specific line, and the angle of that line is determined by the relative value of those two gradients. When I click to a new value of those two gradients, I essentially change the angle of that line. So if these two gradients were equal, I would be along a line that's 45 degrees. Right? And if one is at its maximum value and this one is at 0, then you're reading out along one direction, say on the readout direction here. And so this is called essentially radial sampling. You can see that there's an issue with radial sampling in that you get many, many data samples close to this point in the raw data space, and this is the origin or the center of K-space, or the DC value. So you're oversampled at the low frequencies and you're undersampled out at high frequencies, high spatial frequencies. This has obviously a very strong cousin in CT imaging, right? Because this is essentially the way we were doing CT imaging, except as opposed to we were doing by the, we were sampling projections through the sample along different angles, right? But the Fourier transform of those projections should be a sample through the Fourier transform of the object in CT. So normally you have to regrid data that looks like this to get it on a uniform grid to reconstruct the image. So how do we get all this done in the context of imaging somebody's heart? Obviously, the data, if we look at our signal equation here, this is our primary equation that we're looking at. That's how this is the signal we measure in our preamplifier, etc. This is our object. So if this is the heart in the chest of the patient, one of the problems is it's not something that's stationary, right? MXY is something that's changing as a function of time. There should be a t value here because the shape of the object is changing with time. This equation, while valid, if we made m as a function of t, it gets complicated, to like which t are we talking about when we want to reconstruct a picture. So normally in cardiac MR, what is done is you measure the EKG of the patient, and this is a cartoon of an EKG. You put leads on the patient's chest, and you measure their, here's the P wave, and the QRS, and the T wave. Normally you don't see this in MR. You don't really see a very good P wave with these leads. You see a QRS, which is distorted, and you see a T wave, which is usually distorted. However, if everything's clean and there isn't a lot of noise and stuff like that, you can usually find a fairly consistent trigger from the QRS. And so as time goes on, you can mark where that patient has a QRS at each time point. And we will gate or time our acquisition entirely dependent on when this thing occurs. Right? So if the person had absolutely rock solid heart rate, say they have 75 beats per minute and it just doesn't change, then that's fantastic, right? Then you're going to get a bunch of heart beats that look the same, and we can essentially limit our MRI acquisition to a region inside the R to R in which the heart is essentially the same form or pose. Geometrically, it's not moving. So this is diastasis. This is after left ventricular filling has occurred, and the heart is just waiting for the next beat. And so during that time, we can try and acquire as much data as possible and fill up our raw data matrix or the K space, the Fourier space, and then wait for the next heartbeat and then fill up more of that K space and wait for the next heartbeat and fill up more. And so we're segmentally filling up that raw data space, and that segmentation is triggered by the patient's own heart rate. So if we want to make images at each time phase during the R to R interval, what we can do is we can perform repeated MR experiments for, say, 32 heartbeats, and we'll make a picture of this window, we'll make a picture of this window, and this window. And now we've got 9 separate windows across the R to R interval, and we can make 9 separate pictures, play them back in a movie, and you have a movie of that person's heart beating, right? If we want higher temporal resolution, we can just make each one of those windows more narrow in time. And so if this was, say, 100 milliseconds, this window, and we just drop it to 50 milliseconds, then we have a sequence of images in which it's a higher temporal resolution. However, if we're assuming now we can only take 50 milliseconds of data, it's going to take it twice as long to make these pictures as it does to make these pictures. Because we can't use all of this 100 milliseconds to fill up our raw data space. Now we only have 50 milliseconds. So we're going to take twice as long to make this one, or twice as many heartbeats. So you can ostensibly make very high temporal resolution MRI movies upwards around 25 millisecond time resolution, 30 milliseconds per movie. However, to do that takes 16 to 32 heartbeats, right? Because you have to basically have a lot of heartbeats to use these small windows to fill in your data. So it's kind of your decision as a clinician, like, do I need high temporal resolution data, right? Or do I need to scan this patient in a fewer number of heartbeats? That's the balance there. The other thing you can do is, if we take, some raw data here and raw data here, I can re-bin all of this raw data such that I have temporally use the data from this window and this window together to make a third window. And it centers up the time window. There's still the same width. We're still getting the same amount of raw data, but we're just shifting along and resampling this set of acquisitions. That's called view sharing. Obviously, these frames here are not independent from these frames. So it's not a true increase in resolution. You're not going to see an independent event. It's basically one way of interpolating your data across time. It's often done, it's called view sharing. So here's some examples of what raw data looks like and what its image looks like. All right, so this is remember that S of t, each one of these S's is an amplitude and a phase in the Fourier space, and the 2D Fourier transform of that data gives us this thing, right? Which is our mxy that we had in that equation. One way of increasing the time, or decreasing the time it takes to make a picture is just take less raw data, right? And so if we decided, you know what, let's cut out all of this raw data and we'll cut out all of this raw data, let's just look at this central part. It's like 1/8 of the time. So let's look at that, and it seems like most of our signal power is here because it's highly concentrated in the center. When we look at the image that results, the Fourier transform of this, it looks like this, right? And as you might expect, it's very blurred in this direction, right? So we don't have raw data out here at the high values in K-space in this direction. So when I go through and I look at edges, they're very blurred when I look at the profile of the edge this way compared to up here. So if you look at the cerebellum, you really don't see any of this detail that we had up here. Right? So it's an easy trade-off. You can say, I'm going to stop taking data now and reconstruct with the data you have in hand. And sometimes you get a lower resolution image if your data is collected down in the center. An interesting form of imaging contrast in cardiac imaging occurs when you use a spin echo image in and around the heart or in and around vessels such that the vessel is penetrating the two-dimensional imaging plane. So here is the ascending aorta, this is the descending aorta, right? So blood is going away from us in this region, and it's coming right at us in this region, right? And so let's look at a simple pulse sequence in which we do a slice selection to produce this axial imaging plane, and we're going to do a 180-degree pulse to produce a spin echo. When we do the slice selection, everything in this slice, all the magnetization vectors go into the transverse plane, and they're all ready to create signal to make an image. However, if this is a cartoon of our transverse plane, there is some of the magnetization vectors that are in a vessel. Let's say this vessel here. By the time we go and apply the 180-degree pulse in this plane, those spins have moved out because they're flowing. And so these are brand new magnetization vectors that have come down the vessel. And all they have seen is a 180-degree pulse. And so that is equivalent to making an inversion pulse, and they don't produce transverse magnetization, and they don't produce signal. And so you get black or zero signal or close to zero signal in the vessel. Okay? This is called black blood imaging, and it produces very nice contours of things like large vessels. In contrast to that, and we haven't done T1 contrast yet, but when we look at it, if you pulse, here's our imaging plane, let's say it's this axial imaging plane. If we're acquiring data with RF pulses and readouts, and the time between those pulses is set to generate a certain amount of longitudinal recovery, such that we get a brightness proportional to T1, what happens is when we apply an RF pulse here, if these spins have not seen any previous pulses, they will give you a very large signal because they basically haven't been pre-saturated. And so new blood that moves into your imaging slice for each one of these pulses produces a very bright signal. So you get exactly the opposite effect with this pulse sequence. So now we're not using a spin echo. We're just using a constant set of RF pulses to hit this transverse plane. And the new magnetization vectors that are moving into the plane give you a very bright signal. So you can flip the contrast just by changing the pulse sequence. That's called bright blood imaging. So here's some different contrast images using spin echo. Again, the blood moving out of the imaging plane doesn't give you any signal. And the blood that's moved in has only seen the 180-degree pulse, and so it doesn't give signal. So you get this nice black blood. In the same heart, when you do that gradient echo experiment, now we have bright blood imaging. And then we can generate, if we produce or if we make images with much shorter delay between the radio frequency pulses, we can enhance that contrast, that bright blood to myocardium contrast. It gets even brighter. And this is called steady state free precession imaging. This is gradient echo imaging, and this is spin echo imaging. And this is 3 out of about 50 different contrasts that you can generate with MRI, which is one of the confusing things about MRI when you're teaching it to residents and new students and things like that. It's just a huge variety of pictures that can be achieved by changing the pulse sequence. So these are 3 of the most common pulse sequences used. Let's see where we're going here. Okay. What we'll look at briefly is looking at concentration kinetics as measured with MR, and it's a very simple experiment. It's much like the nuclear medicine experiment where you inject an agent into the patient's vein, and then you watch the signal intensity as a function of position in the heart and see whether or not the agent gets there and how long it spends there. And so if we inject a contrast agent into the patient, we'll see why this contrast agent makes the signal go up. It makes the signal much brighter. And we look as a function of time at the left ventricular blood pool. It gets very bright and then decays away as that contrast agent flushes out of the left ventricle. Normal myocardium may have a response that looks something like this, in which the signal or the contrast agent concentration goes up and then it gets washed out in a normal fashion. And it turns out, and I think we're going to see more of this today in more detail, right, is in abnormal tissue or in infarcts, this contrast agent has difficulty getting washed out, and so it remains in tissue that has an infarct. And it gives you a much higher concentration of the agent in the infarcted tissue than in the normal tissue at about 10 minutes. And so you can see very nice pictures of where infarcts are using this contrast mechanism. And so here's some example pictures of that bright signal there is after a contrast agent has been injected, and you image about 10 minutes later and you see normal myocardium, the contrast is washed out, and here the contrast did not wash out, and it produced a very high signal with the T1 weighted image. So I think that's probably a good place to stop, since you guys, I think, are going to talk more about this, right, in detail, which is terrific. And so let's get on with that.